Hey guys, welcome to chapter 3.5. In this section, we're going to talk about the transformations. This is all about equations that get transformed. This is considered a graphing technique, obviously, but you can also describe it without even looking at the graph by observing the equation, okay? So, we're going to just do the exploration, and we're going to figure out how this works, okay? So, part A is asking us to graph, or sketch the graph of x squared, so we're going to go ahead and do that. So x squared looks something like this. Parabola, right? Oops. Okay, that's pretty bad. I'm going to try one more time. Okay, good enough. All right, so that's what the parabola looks like, x squared. And then it's asking us to go ahead and graph x squared plus 2 on the same picture, on the same grid. So I'm going to go ahead and do that. And I want you to look at these two graphs. So this is x squared, okay, plus 2. I graphed it for you. And the blue is just x squared. And I want you to ask yourself, what has happened between these two graphs? What changed? And I hope you guys see that the change is simple. That the graph, what is the connection between the graphs? The graph, literally the graph went up. So the equation y equals x plus 2, okay, shifted up by 2 units. You guys see that? See this point here? Now it's here 2 units up. See this point here? Now it's here 2 units up. This point here? Now it's here 2 units up, etc., etc., etc. So the entire graph literally moved. It shifted. That's what you're supposed to see. And can you tell how the equation changed? I hope you can see what happened. The equation changed because I added a number to the equation of x squared. So let me ask you guys a question. If you saw x squared, and let's pretend it said minus 5, what do you think would happen to the graph? It would take the x squared and shift it down 5 down here, and then it'll look something like that. So this would be x squared minus 5. It would shift down. It would shift down by 5 units. Okay? And I hope you guys get the idea. And this is actually true not just for x squared, but for any equation. You guys ready? Check this out. If I said the original equation was the square root of x, and then I said, okay, great, now take square root of x and add 4 to it, how would that change? It would change by shifting the graph up 4 units. In other words, if the graph looks like this originally, it goes up 4, and now the graph looks like that. This is square root of x plus 4. This is just square root of x. We agree? What about if I said y equals to the square root of x minus 7? Then this one would go down 7 units. Okay, that's for the square root of x. Is that true for every equation? Yes, literally every equation. Check this out. Let's do the reciprocal one. That's the reciprocal equation, right? Okay. If I said y equals to 1 over x plus, I don't know, 5. Okay, what just happened? The graph went up 5. What if I say y equals 1 over x minus 2? The graph went down 2. In other words, whatever is adding or subtracting to the original equation, that's going to be what we call a vertical shift. Okay, it goes up or down depending if it's adding or subtracting. And that's what the first thing is all about, okay? So, and then you don't have to, so then the notation that you see here is very important. No matter what the equation is, f of x means the equation, right? No matter what the equation is, if I add, let's say, 6 to it, this means the equation is going to, the graph is going to go up 6 because I'm adding 6 to the equation, okay? If I took the equation and I subtracted 1, that means it's going to go down 1 because I'm taking away 1 from the equation. So you can write it as a function notation, Or you can quite literally just put an equation, and it doesn't make a difference. The concept's the same. So the general concept is, if you have an equation and you add a number, it's going to be shifted up that many units up, okay? And if you have a function and you subtract a number, it's going to be shifting down, I guess you can say upward and downward, whatever, that many units. That makes sense? All right, so vertical shifting is all about adding and subtracting to an equation. Okay. What about horizontal shifting? Horizontal means going left to right, right? Well, how about that one? How does that work? Okay, let's find out. We're going to find out by evaluating this graph we have here, okay? So I'm going to evaluate the graph, and then we're going to go ahead and see what happens, okay? So the equation is f of x. We see that? And then they're now going to make us do f of x minus 1. They're going to take away 1 from the x. Now, they're calling this a new equation. They're calling it g. G is x minus 1. But we're going to go ahead and just focus on this, okay? So when I plug in negative 1 into here, it's going to be f of negative 1 minus 1, right? Which is f of negative 2. We agree? And f of negative 2, according to this, f of negative 2 is equal to 2. Perfect. So let me plug that in. When x is negative 1, the solution is 2. Why? Because when I plug in negative 1 into this x, it gives me f of negative 2, which happens to be 2. So when I use negative 1 into this equation, the answer is 2. So when I plug in negative 1, the answer is 2. How about when I plug in 0? Okay, f of 0 minus 1. Remember, I'm plugging in 0 into this equation. 0 minus 1 is negative 1, right? So f of negative 1. F of negative 1 is 0. So when I plug in 0, I get 0. So 0, 0. How about when I plug in 1? Well, f of 1 minus 1 is the same thing as f of 0. Remember, I'm plugging 1 into this equation. 1 minus 1 is 0. And I use this one to find what f of 0 is. F of 0 is negative 2. So when I plug in 1, I get negative 2. So I get this point. I'm going to plug in now 2. F of 2 minus 1 is the same thing as f of 1, right? Because 2 minus 1 is 1. And f of 1, according to this graph, is negative 1. So when I plug in 2, I get negative 1. Finally, I'm going to plug in 3. F of 3 minus 1, right? I'm plugging it in here. Don't forget that. It's going to be the same thing. 3 minus 1 is the same thing as f of 2, which I'm going to use this one. F of 2 is 0. Okay, so then when I plug in 3, I get 0. I'm going to connect the dots. Now I'm going to ask you, what just happened? The graph, did it go up or down? It didn't, right? Did it go left or right? You should have noticed the graph went to the right. Well, how many units did it go to the right? It went 1 unit to the right. Do you see that? So the graph shifted horizontally, right? I'll just say right 1 time. 1 unit, whatever. You guys notice that? We're going to do another example. Because right now you're thinking, I don't know, that's confusing, right? Well, it goes to the right, but then it says here, if I'm not reading correctly, it says x minus 1, and that's a little confusing, right? Okay, fine. Let's do another example, and let's see if we can find a pattern. And as soon as we find a pattern, I'll show you guys how to interpret this, okay? So let's see. Let's try plugging in f of x plus 2. Like we're gonna graph this one. So the original graph is given here. We're gonna use this one. So when I plug in negative 4 into this x, it's gonna be negative 4 plus 2, which is the same thing as f of negative 2. And f of negative 2 is 2. So when I plug in negative 4, I get 2. Negative 4, 2. When I plug in negative 3 into here, I get f of negative 3 plus 2, which is the same thing as f of negative 1. And then f of negative 1 is 0, right? So when I plug in negative 3, I get 0. I'm going to plug in negative 2 in there, so f of negative 2 plus 2 is the same thing as f of 0. So plugging negative 2 is equal to f of 0, and f of 0 is negative 2. So plugging negative 2, I get negative 2. Negative 2, negative 2. And we're plugging negative 1. F of negative 1 plus 2 is the same thing as f of 1. And f of 1 is negative 1. So So when I plug in -1, I get -1. So -1, -1. And when I plug in 0, f of 0 plus 2 is the same thing as f of 2. So then I'm going to plug in, I'm going to figure out what f of 0 is, f of 2. Did I say 0? Sorry. So f of 2 is 0. So then when I plug in 0, I get 0. Boom. What just happened? Let's look at the picture and see if you can tell me what's going on. I hope you can see that the graph went to the left now. Do you see that? How many units it goes to the left? It shifted left 2. Well, let me put shifted, right? I guess that's fine. Shifted left 2 units. Now, if you can see what's happening here, when I add 2 to the x, it goes left. When I subtract 1 from the x, it goes right. And it goes the number of units to the left or right by whatever amount it's subtracting, right? And that's the goal, okay? When you subtract a number from x, the graph actually is shifted to the right, shifts right h units. But if I add a number to the x, it's going to shift or shifts left h units. I'm going to give you plenty of examples now so that it can really drive the concept. Just make sure you don't have no confusion here. We're going to start with the x squared equation. Okay, because everything here is in function notation. Now we're going to actually put examples with the equations. How do you add or subtract to an x if you have an equation? Simple. I add or subtract to the x itself. So this is now adding 1 to the x. But it's still being squared, right? What's happening there? Well, it's because I added 1. It's not going to the right. It's actually going left 1. See how this works? What if I decided to subtract, let's say, 3 from x? What's that going to do? It's because it's subtracting, it's going to go to the right 3 units. Now, if you notice, when you're moving left to right, it's always the opposite. And you're asking, how come? Why is it the opposite? Why does it go left when I'm adding 1 or go right when I'm subtracting 3? Well, the reason why is because the center of the graph is 0. So what would be the 0 for this factor? The 0 will be -1. And -1 is to the left. That makes sense? Because if you want to plug in the 0, that means you have to let x be -1. Well, -1, here's 0, here's -1. -1 is to the left of 0. So you go left, how far is it to the left of 0? It's far, it's to the left by 1 unit. What's the 0 of x minus 3? The 0 of x minus 3 is positive 3, which is to the right of 0 by 3. What you're doing is you're shifting the 0, okay? So that the solution of this 0 is going to be the new center, right? It's normally centered at 0, but now, and you're thinking, why is it centered at 0? Because when I plug in 0 and x squared, what do I get? I get 0. But once I have it something like that, what would I have to plug in to center it to 0? I'll plug in a positive 3, which is to the right of 0 by 3 units. That's the idea. It shifts the graph to the right. Let's do another example, another type of equation. Let's say the square root of x. Okay, how would I be able to fix and make that go left or right? Simple. Check this out. I'm going to add 2x itself like that, x plus 4. And it's still inside the function. It's inside whatever x is, it's going to belong to that. This is not the same thing as square root of x plus 4. Look at the difference. On the one hand, the plus 4 is inside where the x is, and the other hand, it's outside the square root. It's outside of the x. So because it's inside happening to the x, it's going to be a horizontal shift. In this case, it's going to go left because it's adding. It's going to go left 4 units. So if I were to, let's say, subtract 8, this one is going to go to the right 8 units. You ready? I'm going to do reciprocal graph, y equals 1 over x. If I said y equals 1 over x plus 4, this one's going to go left 4 because it's adding. See that? What if I say y equals 1 over x minus 5? then this is going to go to the right 5 units because it's subtracting. Now I'm going to give you a tougher one. You guys ready? Let's do a different equation. Let's do the cube root. Why not? Okay. I'm going to do both. You guys ready? Y equals to the cube root of x plus, I don't know, 6 plus 4. What's happening here? Well, the plus 6 means it's going left 6, and the plus 4 outside of the equation means it's going up 4. That's how you describe the motion, okay? That this is a shifting transformation. Let's do another example. Let's do cube root of x minus, I don't know, 10 minus 14. 14, why not? This means inside here, it's going to the right 10 units, and this outside minus 14 is going down 14. That's how you interpret these. So I hope this is making more sense, okay? The more practice, the better, the easier. All right, now we're done with shifting up and down, left and right. Now we're gonna go into another type of transformation. So this type of transformation is known as a translation. Okay, you don't have to really be worried about the name, but a translation just means you literally are just moving the graph around. Excuse me, you're not actually doing anything to the shape of the graph. You're just moving it around. The shape is consistent. Now we're going to talk about stretching a graph. Stretching it vertically, stretching it horizontally. That's what we're going to talk about. So, they're asking me to graph x squared. I'm not going to. And the reason why I'm not going to is because it's a lousy example of showing shifting. And I'll explain. Actually, you know what? I will do it, but I won't do it on this picture. I'm gonna do a different one. Okay? I'll do x squared here. So here's x squared. Pretend this is x squared. And then I'll do the rest of them later. But before I do that, I want to show you what's happening. Okay? With a completely different graph. So we're gonna do a semicircle. Boom. It can't do a full circle because then it wouldn't be a function, right? We're describing, all of chapter 3 is about functions. So we're describing transformations of a function, okay? Not of anything. So this is gonna be a semicircle, okay? We'll call the semicircle, we'll just say this is f of x. Okay? Now, look what I'm going to do. I'm going to double the equation. I'm going to double f of x. What does that mean? If I double f of x, like it says here, that means I'm going to make it twice as tall. I'm going to increase the height by double. So instead of the biggest height being 3, if I double it, now the biggest height is 6. However, what's the height at 0? When I double 0, I stay 0. So it's gonna get stretched. You see how that works? It's not a bigger circle, or semicircle, it stretches. So it's no longer technically half a circle anymore. It's like half an ellipse, right? Or half an oval, whatever you want to call it. So it's gonna stretch open until it reaches double of the highest point like that. And the orange I just graphed is now 2 times f of x. Okay? What if I decide to divide it by 2? Or take half of it off? What if I have the original f of x and I multiply by half of fx? Meaning I cut the height in 2. So instead of the height being 3, the biggest height would be 1.5, right? Because that's half of 3. So everything will shrink, will vertically shrink. So this blue would be 1/2 of f of x. So notice what's happening. When I multiply outside to a function, when I multiply the equation outside with a big number, like 2 or something, let's suppose I multiply by 3. Let's just do 3. So if it's at 3 and I multiply that by 3, it goes as high as 9. It goes way up there. So this would be 3 times f of x. It's 3 times as big. I hope you realize, I hope you're seeing that the graph is going to stretch when you multiply the equation by a big number, and it's going to shrink when you multiply the equation with the small number. So let's do a quick example. Before I even do x squared and try to show you a visual of it, let's pretend the equation is square root of x, okay? Now I'm going to go ahead and do this. I'm going to take square root of x, I'm going to triple it. What happened? Did it stretch vertically or did it shrink? Hope you can say that this was a vertical, and I have to say vertical because there is a difference between horizontal stretching and vertical stretching. Horizontal stretching, you know what? I'll just do an example. I have a computer, right? So this is a vertical stretch, okay? A horizontal stretch will look like that. So there's a big difference between the two, you know what I mean? So I'm gonna leave this little image here. I might use it later for more demonstration, but for now, this would be a vertical stretch by a factor of 3, right? By a factor of 3. Factor means it's multiplying, right? It's multiplying by 3. So that's the idea. What if it said y equals 1 over 5 square root of x? So the question is, what if you're multiplying by a small number? Then it'll be a vertical shrink or compression. I like to call it shrink by a factor of 1/5, right? Whatever. I'm just not gonna write it. You guys get the idea. Now you're thinking, okay, great, that sounds fine, but how do I know if it's gonna stretch or shrink? It depends on what you're multiplying. If you're multiplying by something bigger than 1, it's gonna stretch vertically. If you're multiplying by something less than 1, like a decimal, it's going to shrink vertically. Okay? That's the idea. So if you're multiplying, if this a, whatever you're multiplying, if this factor is bigger than 1, then the graph is going to stretch vertically. And since they're using the word compression, I'll continue that. If the number is between 0 and 1, so it's a decimal, right? 0.1, 1 over 2, whatever, some fraction, then it's going to compress or shrink vertically, however you want to look at it. So then the graph of the original is compressed and stretched. Okay, so I have to make sure it's in correct grammar, right? So let's do another example before I do this one. So let's do 1 over x. Now, you know what? Let's do a common one you're going to see. The best one is square root of x, but whatever. Let's just say x cubed. So if I say, I don't know, 7 times x cubed, this is a vertical stretch. Hope you guys realize it's a stretch because it's bigger than 1. Okay? If I say 0.7 x cubed, then it's a vertical shrink because this number is between 0 and 1. It's less than 1. Okay? Now, I told you I was going to draw it. And the reason why it's really difficult or a little kind of silly to show you visually how you stretch vertically a parabola is because a parabola doesn't have a defined height. The parabola is already infinite, right? It goes up forever. So how do you stretch an infinite graph? What that means is so it goes up forever, right? It never ends. But if you stretch it vertically, it's going to get up there faster. So it's going to look like this, right? It's going to get, if you're stretching it, you can imagine it going higher, much faster. So it looks like it actually squeezed, but it's technically stretching. That's why I don't like that. Here, you can see the stretch because it's not getting skinnier. It's getting taller. In this parabola, since technically it's infinitely wide, it never gets skinnier because it's infinitely wide. That's why I don't like this example, because it looks like it's getting skinnier, but it's not. It's just getting taller. So, do you see how it did not get any skinnier? It just got taller. You're thinking, what do you mean it looks skinnier? Nope, it's the same width. Okay? If the diameter, if this from here to here, this distance was 1 inch, and I do that, then the biggest distance is still 1 inch. It's not any wider. It's just a lot taller. And that's what's important. I want you to understand that. Or if I shrink it, It's still 1 inch apart from here to here, but it's not, it's actually shrunk smaller. So the height changes, okay? That's a very important concept to keep that in mind. That's why I don't like the infinite graphs, because technically it looks like it's getting skinnier, but it never does. It never gets skinnier. It just gets taller or shorter. Alrighty. So this is for vertical stretching. Notice I multiply to the equation. So I want to, before I go into the next one, I want you to see this. Y equals to 5 times square root of x plus 2. Notice how this 5 is multiplying outside the equation. This plus 2 is is adding outside the equation. Both of these types of transformations are vertical kinds, okay? This is a vertical stretch, and it vertically goes up. See how it's all happening outside. If I wanted to stretch or shrink horizontally, if I wanted to do this, what do you think I'm going to multiply that x to? Multiply that number to. Do I multiply a number outside of the equation, or do you think I'm going to multiply it into the x? If you said I'm going to multiply it inside to the x, you're correct, and you're going to learn that now. Okay? All right, so this example here is asking us, they give us f of x in function notation, and they want us to graph f of half of x. So when I plug in -4 into half x, so f of half times -4x, half of -4 is -2, and f of -2 is 2. How about when I plug in -2, right? So half times -2 is -1, and f of -1 is 0. How about if I plug in 0? Well, half times 0 is the same thing as f of 0, which is -2. How about when I plug in 2? F of half times 2 is the same thing as f of half of 2 is 1, so f of 1, and f of 1 is -1. How about if I plug in 4? F of 4 times, or half times 4, is the same thing as half of 4 is 2, so f of 2 is 0. Now I'm going to plot these points, okay? So when x is -4, y is 2. When x is -2, y is 0. When x is 0, y is -2. And when x is 2, y is -1. And when x is 4, y is 0. I'm going to connect the dots. What just happened? And by the way, I'm going to put the equation. This is half of x, and the original one right here, this is the original f of x. What just happened? What do you think just happened? Did it get taller? Does it actually get taller? Does it get shorter? I hope you can see it does not get taller. Okay, the length of this, the range from -2 to 2 is still the same for the blue. For the black line, whatever, the original graph that's there, and the green one I just drew. They're exactly the same. The range does not change. Do you see that? It's from -2 to 2 for both the green and for the original black, the little diagram there. So how did it change? You notice it stretched horizontally. So then, wait a second. So then when I multiplied a half to the x inside the equation, it stretched, okay, and by a factor of, now here's the tricky part. You're going to reciprocate that. You're going to flip that always. So if it's 1 over 5, you put 5 over 1. If it's 2 over 3, you put 3 over 2. You always flip it. So it's going to be a factor of, since it's 1/2, you put 2 over 1. That's how you do it. Meaning it gets twice as wide. And you're thinking, why? Because whenever you're doing something horizontally, you always notice always the opposite. Haven't you noticed that? If you're adding to x, it's going left. If you're subtracting, it's going right. Well, if you're multiplying by half, it's doubling. And if you're multiplying by 2, it's taking half. It gets smaller, skinnier, whatever. You'll see. So it's going to stretch when you multiply by half. We're going to now do 2x, and I'll prove to you that it gets skinnier. But before I go any further, let me show you just an example of an equation. So let's say it's the square root of x again. That's an easy one to work with. and I multiply the x inside by half, it looks like that. This is a horizontal stretch. Okay? When it's horizontal, it's happening to the x. And if you want to remember, is it stretching or is it shrinking? Remember, since it's opposite, you do the reciprocal. What's the reciprocal 1/2? 2. 2 is big, right? So it's going to stretch. That's how you do it. So that means if I saw this, square root of, I don't know, 5, let's put 5x. 5x. This is going to be, I hope you guys realize, a horizontal shrink or compression. Why? Well, what's the reciprocal of 5? 1/5. And 1/5 is a small number, right? So it's going to shrink by 1/5. That's how it works, okay? It's always opposite. Always opposite, okay? It's always flipping on you. It's always the opposite thing, okay? So then now I'm going to prove that this horizontally, that multiplying by a big number is shrinking the graph by this example here, okay? So let's do the example. We're going to figure out what f of 2x is. So when I plug in -2 into 2x, it's going to be 2 times -2. So 2 times -2 is the same thing as -4. F of -4 does not exist, doesn't have a value. It's missing. See that? Okay. How do you know it doesn't exist? Well, let's look over here. Is there a -4 here? The smallest is -2. I can't use -4. No solution. Let me plug in -1. F of 2 times -1 is f the same thing as f of -2, which does have an answer. F of -2 is 2. How about 0? F of 2 times 0 is obviously f of 0, which f of 0 is -2. How about f of 2 times 1? That's the same thing as f of 2, so f of 2 is 0. And how about if I plug in 2? F of 2 times 2 is f of 4. And there is no 4, it's missing a value, so it's an empty set, doesn't have a solution, okay? So I just put empty set. So now I only have 3 coordinates instead of 4, or sorry, set of 5. So I'm going to plug in the 3 coordinates. So when x is -1, y is 2. We'll do it in a different color. How's that? When x is 1, y is 0. Wait, no. When x is, okay, when x is -1, y is 2. When x is 0, y is -2. And then when x is 1, yeah, it was correct. Y is 0. Look at the green graph. How did it change? You saw how it squeezed? That's what I like to call it. Instead of shrink, I like to call it squeeze. Whatever, shrink is fine. Whatever. Shrink, squeeze, whatever you want to call it, it's fine. See how it's squeezed or shrunk? You see that? So f of 2x was shrunk or squeezed. That's I'm going to use shrink. I've been using it for a while. Shrinked or shrunk by a factor of, and then you do the opposite. What's the reciprocal of 2? 1/2. It shrunk. It got half the height. I mean, not the height, the width. It got skinnier. It's always opposite for horizontal. So let's do a couple. So like this is the bottom line, right? Yeah. So if you ever multiply it by a big number, okay, a big number like 5 or something, it's going to squeeze, I guess, or compress horizontally. But if you're multiplying by a small number like half or 1/5, when you flip that, you get a big number, right? So it's going to stretch horizontally. Okay? So let's actually do a couple of examples, actual examples. You'll see how simple this is, okay? So we already did the square root of x. Let's do another one. Let's do y equals to, I don't know, the cube root of x. I guess it's silly to do that one, but whatever. Let's just do it. So we're going to say, you know what? Not the cube root. Let's do x squared. Okay? Look at the difference. Y equals to, I'm going to put 3 inside with x like that. If I do it like that, I deliberately wrote it that way so that you can say it's a horizontal. Now, horizontal, because you have to flip that. Remember, since it's inside with x, you do the opposite. So instead of multiplying by 3, I'm going to multiply by 1 over 3. So that's a small number, right? So it's horizontally shrinking or squeezing or whatever. Okay? But if I said this, y equals to, I don't know, 0.1 x squared. Well, 0.1 is a very small number, right? 0.1 is the same thing as 1 over 10, by the way. So if I flip that, I flip a small number, I get a big number. Remember that. When you flip a small number, you get a big number. So it horizontally stretches. It stretches. Okay? Alrighty. So that's the idea. I hope this is making sense so far. So now we're on to reflections. So we talked about so far, the first thing we learned is translations, sorry, meaning the graph is going to move left to right, up, down. Then we talked about compression or stretching. The graph is going to get squeezed or shrink, whatever you want to think of it as, or stretched, right? And now we're going to talk about reflecting. Literally, the graph is going to quite literally reflect over the x-axis or over the y-axis. Okay, it depends on which axis. It depends on where a negative is. That's what's going to happen. So to show reflection, you have to multiply it by a negative. In functions, multiplying by a negative, multiplying by negative, I'll put -1, means it's going to reflect. That's what it means. Okay, very important. Multiply it by a negative. Whenever you see a negative somewhere, I don't mean subtracting 5. No. Multiplying by a negative. Like, for example, right here. See how it's multiplying by a negative? Or maybe it's this case, in the first case, it's outside. In the second case, it's inside. Now look at this one. It's outside, it's inside. So wherever that negative is, it can be outside the equation or inside. That's what's multiplying by a negative looks like. That tells you what kind of reflection it's going to be. Now I know it's going to be called in right now a reflection about the x-axis or y-axis. I'm going to ask you to think of it differently. Think of it as a vertical reflection and horizontal reflection, and then you can interpret what kind of axis that means. What am I referring to? Like this. Have you noticed, this is a pattern we're looking for, right? Have you noticed that whenever something's happening outside of x, 5, square root of x plus 1, all these outside things happening, these so far have been vertical changes. Haven't you noticed that? And then whenever you see stuff like this, like let's say it's multiplying to the x and then maybe it's subtracting or something inside, haven't you noticed that all these things are horizontal changes? Have you noticed that? Horizontal. If you've noticed that, then that also gives you an idea of where I'm headed. If you multiply it by a negative outside the equation, I just want you, for the sake of argument, to interpret this as a vertical, since it's outside the equation, a vertical reflection. What does a vertical reflection mean? It means that if it's over here, it's going to go down vertically to now be here. Now, vertical reflection, I just give you a quick demonstration, means reflecting over the x-axis. That's what it means mathematically, but it's just easy to understand. A negative multiplied outside the equation is a vertical thing. Since it's a negative, it's reflection automatically. Okay? How about if it's multiplying to the x inside? Well, guess what kind of reflection that is? That's a horizontal reflection. Now, that's how I want you to interpret it or visualize it. So that means that if there's something over here, it's going to reflect horizontally to this side. And that's going to be over the y-axis. So technically, it's over the y-axis. It's a type of reflection. So in other words, if I had a picture, like let's say it's over here, and I said, oh, I want to reflect it over the y-axis, now the picture will look like this. You know what I mean? So how do I do that? How do I reflect it horizontally? I put a negative inside the x. That's all I got to do. And it reflects the picture. It's pretty cool. So in the case G3, since the negative is outside, it's going to be vertical reflection. Okay, that's a reflection over the x-axis. Okay, and then finally, the last one here is a negative inside with the function with the x. It's literally next to the x, so it's going to be a horizontal reflection, which is a y-axis reflection. Okay, Yeah, I'm going to fill this up, and then I'm going to give you a couple of examples in terms of illustration, what that looks like, okay? I know there's no pictures, but I want to show you quickly. So if there's a negative outside of the equation, that's going to reflect vertically, okay? Vertically means x-axis, okay? This is a vertical reflection. If it's a negative inside where x is, that's going to reflect horizontally, right? That's a horizontal reflection, and horizontal reflections are over the y-axis, okay? Let's do a couple quick little illustrations. The very easy one to do, the best one to do, is the square root of x. This is the equation of the square root of x, okay? If I decide to put a negative outside, it's going to reflect vertically. It's going to go, that doesn't look such a good word, whatever, something like that. This is a negative outside. This is a vertical reflection. It reflects literally going up to down. That's a vertical reflection. If I decide to reflect it horizontally, like this, so from right to left, this means there's a negative inside. So there's all the three graphs, okay? They're all different. This is not one graph. This is three different graphs, okay? The original graph is this one. This is the one that when you put a negative outside, and this is the one where you put negative inside, because I'm reflecting in different directions, okay? Either horizontally or vertically. Over the x-axis or the y-axis, however you want to interpret it. That's what it looks like, okay? All right, so this seems to be like a summary. All right, let's go ahead and try to see if we can figure out the summary. So if I am adding, it says draw the graph of f. Oh my gosh, I'm not drawing. So it's just going to go up, right? When you're adding a number outside the equation, when you're adding it to the equation, it's going to go up by k units. If you're subtracting to the equation, it's going to go down k units. I'm not going to draw it. There you go. And then what about if I'm adding to the x? If I'm adding to the x, it's going to go left k units. If I'm subtracting to the x, it's going to go right k units. If I multiply it by a number outside and it's big, it's going to vertically stretch. And then if I multiply, okay, it's missing the case. Okay, whatever. It's only the case when a is big. What about if I'm multiplying to x and again a is big? It's the opposite. A big number when I reciprocate is small, so it's going to horizontally shrink or squeeze, right? If I put a negative outside, we just learned about it, it's going to be a vertical reflection, right? Which I'm going to say that's, I want you to remember, vertical reflections over the x-axis, and then horizontal reflection, which it's inside, is over the y-axis. All right, this is just you can draw it if you like, but this is just, you can know how it works. Okay, so now, okay, we have 4 examples, and so I'm not going to actually draw. I'm assuming they're going to ask you to use a graph and obtain. Yeah, I'm not going to draw. I am not. That's just going to take it too long. What I really want you to do is just to learn how to be able to figure out what's happening, okay? What's happening here? What's going on in terms of the transformation? Now, I want to keep in mind there is an order to transformations. You always do multiplication. It's PEMDAS, basically, right? So you multiply first, and then you add and subtract. If you have exponents, whatever, but in terms, there's only two things you're doing technically. You're either multiplying or dividing, whatever, and then adding and subtracting. So first thing you do is multiply, right? You first describe what's going on here, that's multiplying, and then you can describe what's happening here and here. Now, I'm not really asking you to graph it, but if you did, you'd have to first reflect it, stretch it vertically, move it left, and go down. So that's how it would look like. I'm not gonna bother. You know what the heck? I'm gonna do the first one only so you guys can see. Now, this is how you interpret. Step 1. You know what? I'm going to start with the outside. What's happening? What's this minus 3 outside the equation doing? What's this doing? This minus 3. I hope you guys realize this minus 3 is subtracting 3 outside, meaning it's going down 3. It's a vertical translation. Let's look at this plus 1 inside with x. What's happening there? When you're adding 1 to x, you're going to go left 1. If it was subtracting 1, if this said minus 1, then you would go right. Now here's the part where everyone always makes a mistake. They think of this as negative 2. Never say that. The 2 is one number, the negative is another part. Okay? So the 2 is one thing and the negative is the other. So the negative is a reflection. What kind of reflection? Well, since it's outside the equation square root of x, absolute value, excuse me. Since outside of the equation, it's a vertical reflection. Oops. Vertical reflection. Which means it's over the x-axis. What about the 2? Well, the 2 is multiplying outside the absolute value, right? Outside the equation, the original equation. So it's a vertical stretch. And you're thinking, why is this stretch? Because it's bigger than 1. It's a multiplied by a big number. So that's what's happening. It's having all those effects. It's having, the negative is having a vertical reflection. I'm going to list all 4 things. It has a vertical reflection. Okay. Or reflection about the, over the x-axis. It has, second thing it has, it's a vertical stretch. Okay, it's multiplying by a 2, so it's going to vertically stretch, it's going to get taller technically, but this is infinite graph, so it won't look taller. 3, it's going to go left 1, because it's adding 1 inside with x, and 4 is going to go down 3, because it's subtracting 3 outside of the equation. So if I were to graph it, it would, first of all, it would look like it's going down, and then it stretches vertically. So it's gonna look skinnier because it's stretching vertically, but it's an infinite graph, and then it's gonna go to the left 1 and down 3. So 1, 2, 3. It's gonna like start there, and then stretch. Man, this scale is way off. Look how wide it is. So it's way off, but whatever. So it's gonna go like that. Whatever. It'll look something like that. It's not perfect, guys, because I didn't actually pay attention to every detail, but I mean, it's kind of like that. It's reflected down. Always the reflection first, then stretch. You do the multiplication stuff first, and then you go up, down, left to right. So if you reflected it first, and then you stretched it, and then you move left and down, eventually you'll end up with what you have here, okay? All right, how about this one? So I want you to notice in this one, there was 4 things happening. 1, 2, 3, 4. So I had to list all 4, okay? So that's how I did all 4. Here, what's happening? Look at the original equation. Now look at this one. There's a half and a plus 1. There's only 2 things happening, so there's only 2 transformations. Let's describe the half. The half is multiplying outside the equation. Vertical. Now, since it's half, would it stretch or shrink? I hope you guys said shrink. It's a vertical shrink. So I'm going to put vertical shrink. Okay, or compression, whatever. And then what about that plus 1 that's inside with the x? What's happening there? Well, remember, inside the x is left and right, and it's always opposite. Whatever happens inside is always opposite. So the opposite of adding 1 is going to be going left 1. Okay, so it shifts left 1. So in other words, it's going to shrink vertically. It's going to get half the height, and then go left 1. So this point's going to go left 1. This point's going to go left 1, but it's shrinking. This point that's here 4, going to go left 1, but it's shrinking to there. So it looks like that. Okay. Alrighty. These are terrible examples for shrinking because it is getting shorter. That's true, But it's an infinite graph, so technically you can't infinitely get something that's already infinitely tall to get it shorter. That makes sense. But anyhow, let's do this one. This one has, look at the original, x squared. Now it has the 3 is 1, the negative 2 is 2, and the plus 1 is 3. There's 3 things going on. Let's describe all 3 things one at a time. Multiplying 3 outside the equation. Vertical stretch. Since it's a big number, it's going to vertically stretch. Subtracting 2 inside with x. It's going to go opposite, so it's going to go to the right 2. So vertical stretch, right 2, and this is going to go up 1. It's going to go vertically up exactly where it says 1. It's not the opposite when it's outside. It's only opposite when it's inside with the x. So it's going to get vertically stretch. Again, infinite graphs. When I stretch it vertically, it looks like it's getting skinnier, but it's not getting skinnier. So remember that. Please remember that. So it's going to go, so the height's going to get 3 times, right? So it's going to be, if the height is 1, now the height is 3. If the height is 4, it's going to now be 12. It's going to get much skinnier, like this. But it's actually not skinnier, it's just taller. And then it's going to go to the right 2 and up 1. So 1, 2, up. So it's going to go there. This point goes here. This point goes to the right 2, up 1. This point goes right 2, up 1. So I think I have plenty of points there. So it looks something like that. Okay? Something like that. All right, one more to go. So here you go. The original is x cubed. There's a negative inside and a plus 2 outside. Let's see if we can figure out what these are. The negative inside is a horizontal reflection. Negatives are reflection, okay? And a horizontal reflection means it's about the y-axis, right? Now, finally, the last one, the plus 2 that's outside, this is I'll put this horizontal reflection. And this plus 2 is going up 2 since it's outside. So horizontal reflection first, so it's going to go, this right part here is going to look like this, and then this part's going to horizontally reflect like that. So it's going to look like what's in blue, and then go up 2, correct? So at this point will go here, since it was supposed to go there, so this point goes here, looks like that. This part will go here, so up 2, so that goes, it looks like this. It's not perfect, guys, but more or less. Okay? And that's all there is to it for 3.5. So I know this is a very time-consuming long lesson, but I hope that this made sense on how to do transformations. If you have any questions whatsoever, guys, please let me know, and I'll be happy to assist you. Otherwise, I'll see you guys for the next one. Take care.